Hello everybody, in this video I am going to demonstrate to you how to install TSMC 180 nanometer technology files into LT-SPICE and do an NMOS and PMOS characterization. Okay, so first you can go to my web page sanjayvidyadharan.in, and the download section you can download these three files which are TSMC 180 nanometer technology files. There are three different files here. One is the library file which contains the model, and then there is two symbols. Okay, this is the NMOS symbol and this is the PMOS symbol. So these three files are available there. Alternatively, in the same downloads you will find one zip file. You can download it and extract it. You will get all these three files. Okay, after having downloaded that, you can download LT-SPICE and install it. You can go to the LT-SPICE web page and you can download LT-SPICE. It's a free software. Okay, otherwise you can also in the same my download section on my web page there is something known as there is a folder LT-SPICE installation files.rar. okay, so you can download this and you can extract it. Okay, so after having done that, you need to install the LT-SPICE and open an LT-SPICE first. Okay, this is the next step, and from the file tab you open a new schematic. Okay, so you select a new schematic. So once if you click on the new schematic, you will get a window like this. Okay, on that window here you will find something known as it looks like a NAND gate. It is actually an tab to select components. So if you click on that, a window will open out here, and you will find some components are already there here, available here, which is inbuilt in the LT-SPICE, whereas our which we have downloaded 180 nanometer TSMC files, that we need to put in here. That won't be available as default setting here. Now how to put it that? For that we need to note the path out here. So where is this LT-SPICE picking up these symbols, right? These components, this path is given here. So for my particular installation, it is C users mono documents LT-SPICE 17 and then lib.sim. okay, sim stands for symbol. So this is the path. I am going to note down this path. This path is it's not going to change on your PC depending on where it has got installed. So this path will be different for you. Okay, so now for my case, like it says C mono documents, sorry, there has to be let me just change this. There is an LT-SPICE also here. If you see here, C mono documents LT-SPICE documents, and then there is LT-SPICE. That's the path, right? So you need to go to that path out here. So and then this is dash sim, the last is sim. Okay, in the sim you will put these two symbols. Okay, these two, whatever we have extracted, you copy that and you paste it here in this particular folder. Then from this folder you go one level high, so you will reach .lib file. Okay, from lib file, in the lib file there are two folders. One is sim folder and one is sub folder. So you come back to the sub folder. Okay, in the sub folder you are going to paste this library folder. Okay, don't put this lib out here. Okay, this lib file, this is the library file, okay, of the one LT-SPICE. It has got a set of symbols and a set of model files. All the symbols are put in symbol file, and all the symbols are put in the symbol files, and all the model files are put in the sub folder. Okay, so this is our model file. Okay, so this model file we got to put it in the sub folder. Okay, after having put that, then you restart the LT-SPICE. You might have to close it and start it once again. Okay, then a new schematic, you can open a new schematic. Here you will find one tab which is known as the SPICE directive. So you need to click on that. Once you click that, you have to select the SPICE directive. There is one comment also. Okay, but this is not a comment which we are giving. We are giving an SPICE directive. So important that we select the SPICE directive, and then we have to write the type include, no, we have to write here type here dot include tsmc 018.lib. so this is the file, right? tsmc 018.lib. this is the library file which we have pasted there. Now we are telling LT Spice, okay, you have to use this model file, so that is why we write dot include. Okay, having done then, you can close this Spice directive. Okay, after that, once you close that, once you select the component, you will find in the component menu, you will now find CMOS N and CMOS P. So by default you will not find these things. Okay, now this is not a generalized CMOS N and CMOS P. So there is something known as an NMOS and PMOS there. Okay, that is different. Now for our 180 nanometer technology, the name of the symbol is CMOS N and CMOS P. So we can select these NMOS and PMOS from the component and then set the values of W by W and L and do the simulations. Okay, so you can subscribe to this channel also, so that as and when I keep posting some videos, you will get an instant notification. Now I'll show the demonstration aspect of this. Now let me demonstrate to you what I just explained to you. You can go to my web page, which is sanjayvidyadharan.in, and then you have an downloads tab here. I click on that. Now if you see here, there is one TSMC 180 nanometer here, right? So I click on that. I can download these zip files, or individually if I want to download, I can do these three things. Okay, so I download this zip file out here. Go back here. If I want LT Spice installation files, I can click on this, so it will get downloaded out here, right? Okay, so having done that, let me close this. So now I have extracted these two files, and one is LT Spice installation file. So you will find one is LT Spice and 32, and one is 64. So depending on configuration of your PC, you can either download, execute this one, install the 32-bit one, or the 64 one. So you need to install an LT Spice. Okay, after doing that, then in the TSMC folder, if you extract, you will find these three files. Okay, this is to CMOS N and CMOS P.asy. These are the two symbols, and this is the library file. In this library file, the model for the NMOS as well as PMOS, both is available in this. Okay, so these are the three files. So we need to paste these things in the appropriate folder. So let first these two symbols, where to paste these two symbols. So for that, I open LT Spice. So I open LT Spice, I go to file, okay, a new schematic, right, and I click on the component. This is the component menu. If I click on that, it will give me the path. It says C users mono documents LT Spice stroke lib stroke sim. Okay, sim means symbol. Okay, so this is the place where this is the path. I will get this path. So in this path, I am now going and going to paste the symbol files. Okay, so let me close all these windows. Yeah, okay, so I'm going to see, I'm going to see, okay, and then users, it says mono, and then it says documents, and then LT Spice, and lib file. In the lib file, there are several things, sub and sim. Okay, so I open up sim, and in the sim I am going to paste these two. So I already pasted it here. So if you see here, CMOS N and CMOS P, these two symbols I have pasted here. So I go one level up here, I come back to this lib. Okay, I don't paste this lib file here. Okay, what TSMC lib file, I am going to open under the lib. There is something known as sub. So if I open the sub, I will find so many model files are available here. So here I am going to paste. So this TSMC.lib file. Okay, so these things I have to do. Okay, the symbols I have to paste in the symbol file, and the lib file I have to paste in the subfolder. Okay, so this is the path which I get from there. Okay, so with that, now we are ready to. So you might have to restart after pasting this. You might have to restart your LT Spice. Okay, so if you see here, So let me first, already I had open. So this after that you need to write this command, right? Because include TSMC, because by default this library will not, which we have pasted, will not be picked up. So where to write this? So you have a SPICE directive here. I click that, I select the SPICE directive, and then I write a dot include, and I write this entire thing right here. Okay, and then I press OK, it will come here, right? So this is only partially written, you have to write this whole thing here. Okay, so with that, now that library file has been incorporated now here, only then the simulation would run. Now to pick up the components, I have this component menu. I pick up here, I go to, now initially if you find before writing this and pasting those, you will not find this CMOS N and CMOS P. These are the 180 nanometer technology files which we have pasted here, right? But this by default it will have this NMOS, right, PMOS 4. These works on different, they are not 180 nanometer technology files. Okay, that we'll see later on. So for us, these are the two CMOS. Okay, these are the ones which we CMOS N and CMOS P. So CMOS N, this is the symbol. Let me take this symbol and show you how to do the characterization, right? Okay, now body is being connected to the ground, and again I put one more wire out here, and I take the ground from here, I put a ground here. Now I have to give VGS and VDS, so I go back to the component menu out here, and I go towards the end. This here I have something known as voltage, so I am going to put a voltage here, right? So this is the V1 voltage out here, so I am going to connect this voltage out here, right? And then I have to put a ground for this. I'm putting a ground here. I'm going to connect this ground to the negative of this voltage source, and again I am going to pick up one more voltage source. I'm going to put it here. This is V2. Now I'm going to connect V2 out here, right? Now I need to connect a ground here also, so I'm going to connect a ground here also. Now let me just, okay, this body needs to be connected to the ground. Okay, now I have this W and L here, right? So this is 180 nanometer, and the minimum width which is permitted for 180 nanometer is 400 nano. So I can put 400 nano, but let me do an characterization for 1 micro. Okay, width. Okay, let me just put it as 1 micro. So this is the NMOS. Okay, I have put an NMOS out here, right? Now let me do some simulation. So let me change this voltage. Okay, so let me keep this voltage constant. So I am putting it as 1.8 volt. Okay, let me put this also as 1.8, but I can vary this. Okay, now I put both 1.8 volt, because 1.8 volt is the rated voltage for 180 nanometer technology. So I do a right click and I have edit simulation command. Now I am going to do an DC sweep. So what is the source which I want to sweep? This is V1, right? So I am going to write in a V1 here. Type of sweep, you can have an logarithmic, octave, decade, or linear. So linear. Start value is 0, stop value is 1.8 volt, and increment is say 0.1. 0.1. So every 0.1 volt, and it will, let me put it 0.2 here. It will save some time. Okay, so now I am going to do the DC simulation. So let me run it. So I'll get a waveform window. Now I have to plot the current which is going here, right? This stands for voltage. Okay, this red one, like, okay, so if I click here, you see this voltage is going from 0 to 1.8. Now if I have to plot the current is this. Okay, you will find one loop kind of thing. So I click here. So this is the current which is flowing. So let me expand this window here, right? Now so let me just remove this. This is a linear voltage. I'm not interested in that. So this is the current. Now if you see here, it has got an threshold voltage. From point it is moving like this. Okay, you will find this not very smooth. So let me go back here, and let me write it as an 0.5, smaller step size. Okay, So I'll find this curve is now slightly smooth. So this is how this is the ID VGS curve. ID VGS curve, right? So this is for 1 micrometer. Minimum length is 180 nanometer and 1 micrometer. Okay. Now I can put an let me put an marker here. Okay, first and second. So I get 2 markers here. So first marker, I am going to move it here. So I'll find in this window it is 0 volt and 52 picoampere. That means the leakage current here for NMOS is 52 picoampere. And now the second marker, this is going to be the on current, right? I'm going to put it at the highest voltage, 1.8 volt. It gives 600, close to 607 micro. So this is the off current. This is the on current. Okay. Now I can do one thing also. Now I can, if I want to change the width and see what happens, right? And I can do it as an 2 micro also, and then I can do the simulation and find out what is that. Okay. So now what I can do is I can also do instead of changing this voltage, I am going to this is V2, right? So I have changed here, right? And I have changed to a V2 here. Now I am going to change V2 and see what happens. So if you see here, now this is like V2 is changing, right? So this is the drain characteristics. This is known as the drain characteristic. The first one which we saw was the that is known as the transfer characteristics. So this is the drain characteristics of an NMOS. Now if you want to do multiple sweeps and see what is the effect, suppose this is V1, I want to find out drain characteristics for different values of VGS. Okay, so what I do is here instead of giving 1.8 volt, I am within curly bracket, I am going to give VGS. Okay, within curly bracket, that means I am making this as a parameter. Okay, so I give OK. So now this has become an parameter here, and then I write this command. Okay, where did I get this command? Again from here. I click, I write spice directive, and I write dot step parameter VGS. VGS is nothing which is written in the curly bracket, 0 to 1.8. So I am going to sweep this for each run. I am not sweeping it for each stepwise. For each run of V2, I am going to change VGS from 0 to 1.2 and in steps of 0.2. Okay, so that means I will get around 10 plots out here, right? So I do that, and now I run. So if I do that, so now I am getting VDS for each of these VDS. VGS is initially 0 and finally VGS is 1.8 volt, right? So this is how I get an VGS plot. Okay, so this is how about characterizing the NMOS, right? So you can do other things also. You can make this width also as a parameter. Doesn't matter. You can do that also. You can make this width as a parameter. You can keep this constant, and you can do a sweep and find out how does this current varies with respect to the width. Okay, so you can do. You can make this also as a parameter and keep this constant. So all those things you can do it yourself. Okay. So now let me show how to characterize the PMOS also. Let me put it back to 1.8 volt out here, and let me change this back to we'll compare the transfer characteristics of a PMOS and an NMOS. Okay, so now I go to the component menu and I select an so don't select this PMOS 4. Okay, for 180 nanometer technology we have put a specific symbol. So that specific symbol is CMOS P. So select that. Okay, now I'm going to put that there. Let me make some space for this. I can go edit, duplicate. So I'm going to put one source here. I'm going to connect it here. Edit. I'm going to pick this voltage here. I'm going to put a source here. this is a PMOS. So I am going to connect these here, and also see for PMOS I need to change a source gate voltage, right? So I am going to move this voltage out here, and I'm going to do this interconnection out here. I'm going to make this connection out here, right? So I'm going to now I'm going to change, I'm going to change this voltage, right? And then plot the output and currents out here, right? So let me do that. So now I'm going to for PMOS characterization, I'm going to change this voltage, so it is a V3 out here. So I'm going to click out here, I'm going to put it as a V3. Okay, and then here also let me put it as an 180 nanometer, and then width as 1 micro. Okay, I think that is good enough. So let me run the simulation. Let me run the simulation once again, and then plot the current here. Now you will see this is the current plot for the PMOS. Now if I put in a marker out here, 1 and 2 markers. Okay, so one marker I'm going to move it here. So I'll find that 22 picoampere is the leakage current in the PMOS out here, whereas the on current is something close to 287, right? There we found it is slightly more than 600. So obviously for the same width we'll find that NMOS has gotten more current than the PMOS, right? Almost double the current. So that is why when we learn further, we'll see that wherever we have to use NMOS and PMOS in conjunction, we will generally use the PMOS width to be double of NMOS, so that this current remains the same, so that the rise time and fall time remains the same. You'll see that the PMOS current is only 287, whereas that of the NMOS we found it as 600 for the same length and for the same width. Okay, so that's how we can do the characterization of PMOS and NMOS. Okay, you can do the drain characteristics. Here we saw the transfer characteristics. You can try out the drain characteristics also for the PMOS. Okay, thanks a lot.